Hi everyone, I'd like to welcome you to this webinar today, which we've titled Future Stars of Geology, Geophysics and Geoscience. We have a full list of presentations from university students, postgraduate students who are going to be presenting on their research they're doing. So it's a great opportunity to see some upcoming geoscientists and future stars of the geoscience industry. My name is Matthew Greenwood. And I'm the manager of the regional compilations team at the Geological Survey of Queensland. Firstly, I'd like to acknowledge the Yugara and Turrbal people, the traditional custodians of the land which I'm joining today from Brisbane or Mianjin. I'd like to extend that welcome or that acknowledgement of country to all of the traditional lands from which our webinar presenters are joining from today and our participants, and any Indigenous or people who are on our call today. We have a range of presenters from universities, both interstate and international. And our first presenter is Chris Emproto from the University of Michigan. Now, it is 2 a.m. in Michigan right now, so rather than asking Chris to present live, he has pre-recorded a presentation for us. So first up, I'll be sharing Chris's presentation about while I fire it up. Stable isotopes, unraveling the origins of Cloncurry IOCG deposits.
Hi everyone, my name is Chris Emproto. I'm a PhD candidate at the University of Michigan in the Adam Simon Research Group, and today I'm going to talk to you about some of my research for my dissertation, where I use stable isotopes to unravel the origins of iron oxide copper gold, or IOCG deposits in the Cloncurry District in Australia.
I want to start off by thanking our collaborators. This project would definitely not be possible without the hard work of Ryan Mather, in addition to Linda Godfrey, Ilya Bindeman, Courtney Nyarum, Vladimir Lisitsyn, and my undergraduate assistant James Rausch, who assisted in preparing the samples.
IOCG deposits are structurally controlled iron oxide and copper iron sulfide mineralization that is often associated with regional scale alteration, particularly sodic calcic alteration. And these are really diverse deposits, but they're tied together by their physical and geochemical characteristics. And they're pretty complicated with long mineralization histories. And so they're sort of difficult to really unravel the origins of. And there are a couple of different prominent formation models that are proposed to explain these deposits. There's a magmatic hydrothermal model, which is favored by my research group, in which both the metals and the fluids are from a magma. And then there's also the basinal brine model, where the magma is only the heat driver, and the fluids are basinal brines that leach metals from crustal rocks. And my research group has used stable isotopes to test these formation models, particularly in the Andes and in Missouri. In testing the broader applicability of these different formation models, we decided to look at deposits in the Cloncurry District in Australia, particularly Ernest Henry, which is the largest IOCG deposit in the Cloncurry District, as well as Osborne, which is also in the Cloncurry District, but is interpreted to have a different origin from fluid inclusion data. Now, Ernest Henry is thought to be the magmatic end member of the Cloncurry IOCGs, whereas Osborne is thought to have very little to no magmatic influence and is instead interpreted to represent a banded iron formation that was mineralized by mixed metamorphic and sedimentary fluids. We want to know what are the metal and fluid sources for the Cloncurry iron oxide copper gold deposits, which formation model do they represent, and how does this compare to the Andean deposits that we've already studied? To do this, we're going to use stable isotope geochemistry of magnetite. And magnetite is a very common and abundant mineral in both the ore mineralization as well as the pre-ore mineralization at the Cloncurry IOCG deposits. In particular, we use oxygen and iron isotopes. And oxygen is in everything. It's the most abundant element in the Earth's crust, and it's in fluids and water, and so we can track fluid source as well as alteration, and even things like carbonate contamination, because carbonates have a very different oxygen isotope composition than to magmatic magnetite. And iron isotopes track magmatic versus non-magmatic iron contributions. And iron is a major metallic component in these deposits. And so if we understand where the iron came from, we can understand maybe where some of the rest of the metal load came from that formed the deposit. Iron and oxygen isotopes are used because these have been measured for magnetite from a variety of systems, and so we have a pretty good idea of what the range of magmatic magnetite is. And that's represented on the figure here by this dashed box. And so this is not really like a hard boundary. Think of it more of like a 2 sigma, sort of a confidence interval of what is likely of magmatic origin versus not. And there can be magnetite that has a non-magmatic origin that happens to plot in this box, but magnetite that has a magmatic origin is very likely to plot in this box. And magnetite that had a magmatic origin could be kind of moved away from this box if it's altered by surface waters, or if the magmatic fluids that formed it were influenced by things like carbonates. And from what we've observed from studying Andean and Missouri IOAs, those are iron oxide apatite deposits, and iron oxide copper gold deposits, tell us that the metals and fluids that form these deposits are magmatic hydrothermal in origin. However, when we plot our Ernest Henry data onto this plot, we see that they do not behave like the other samples. The Ernest Henry samples, which are the colored circles here, so yellow is the ore mineralization, that's that magnetite that's interpreted to have formed alongside the copper and gold mineralization, as well as the blue and green dots, which are the pre-ore alteration. Most of the data plot outside of the magmatic origin box, and this tells us that some component of this magnetite is non-magmatic. You can see it's not the oxygen isotopes that cause the data to fall outside of the magmatic origin box. It's simply the iron isotopes. So what this indicates is that Ernest Henry had a significant contribution of non-magmatic iron that may have been carried by magmatic fluids or by fluids that equilibrated with igneous rocks with respect to their oxygen isotopes. To better understand this, I did some geochemical modeling in order to see if a magmatic origin would explain these iron isotope values. Now, the global range of igneous rocks for delta 56 iron more or less overlaps with the magmatic origin box of magnetite, and this is easily explained by, at high temperatures, the amount of fractionation or selectivity between the melt and magnetite is very low. So the composition of magnetite is essentially the iron isotope composition of the magma that it crystallized. And so if we're just going to be crystallizing magnetite from a melt, we would need an iron isotope composition that is far outside of the range of global igneous rocks. And this is still the case even if the iron was transferred from the melt to a hydrothermal fluid, and then from the hydrothermal fluid to the magnetite. And this is because the fractionation, the selectivity of the fluid relative to the melt is essentially the opposite of the fluid to the magnetite. And so the fractionation essentially gets undone when the iron is transferred from the melt to the fluid and then from the fluid to the magnetite. And so even if we have a fluid as an intermediate phase, we still need this iron isotope composition that's broadly similar to the iron isotope composition of the magnetite that we measured, which is far outside of the magmatic origin box and therefore implausible. But what is more plausible is that the iron was instead leached from crustal rocks. And I got this idea by reading a paper where I saw that the iron isotope range of mid-ocean ridge vent fluids, which acquire their iron isotopes through the leaching of the seafloor, can have really, really low iron isotope compositions, low delta 56 iron isotope compositions. And so it's likely that much of the iron at Ernest Henry was leached, and then this is instead a mixing line between leached iron and magmatic iron or iron that was in the protolith. So now if we take a look at the Osborne magnetite, we can see that it's very, very different from the Ernest Henry magnetite. So Osborne are the red circles here on this plot, and Ernest Henry, again, are the yellow, green, and blue circles. So not only does Osborne not match up with Ernest Henry, it also does not match up with any of the previously measured magnetites from IOAs or IOCG deposits in the Andes or in Missouri, which indicates that Osborne is a very, very different beast, even if it's still an IOCG deposit. So Osborne had a major contribution of non-magmatic iron, just like Ernest Henry did, even though the iron is sort of fractionated in the other direction. But unlike Ernest Henry, Osborne also had a major contribution of non-magmatic oxygen. So it's not looking like a magma was very important or even present at all in the formation of the Osborne IOCG deposit. But because the iron isotopes are sort of fractionated in the opposite direction of Ernest Henry, we can interpret that it has a different iron source. So at Ernest Henry, we think that much of the iron was leached. That was the best explanation. But here, that doesn't seem to fit at all. But luckily, we had some clues to help us solve this problem. So Osborne is hosted within a banded ironstone, and the origin of that ironstone was sort of debated. People were leaning towards it being a sort of banded iron formation, a sedimentary ironstone, but there was still some debate about that because of the overprinting of the IOCG mineralization. And so people were wondering if the iron was instead introduced later and if the banding structures were sort of fake banding and not original sedimentary banding. But we can see that the iron isotopes are best explained by BIF magnetite. So they are, again, far outside the magmatic origin box. They're away from the leached iron range that we interpreted from the Ernest Henry data. But the banded iron formation magnetite can have a very wide range of iron isotope values and also a very wide range of oxygen isotope values. I didn't draw a box here because BIF magnetite essentially eclipses the range of oxygen isotopes here, and so the ranges that we see from our data are quite plausible compared to BIF magnetite. Now we've taken a stab at where the metals came from as well as where the fluids came from. We can sort of get a better idea of where the fluids came from by utilizing triple oxygen isotopes. That's just where we measure 17 oxygen as well as 16 and 18. And by using these two different isotope ratios, we can get high resolution on the fluid source. And so that's what I did at Ernest Henry. And you can see that these are pretty much outside of the magmatic origin box again, but this could be because there's a mixing between other fluid sources. And the direction that the data are moving suggests that there is a metasedimentary or evaporitic input that is, again, pulling the data outside of the magmatic origin box. And so we can infer that Ernest Henry had a fairly complex fluid history, including isotopic exchange with metasediments, particularly carbonates that have really high delta 18 oxygen values, as well as potentially magmatic fluids. Now, if we go over to Osborne, we can see that once again, these two are diametrically opposed. Osborne exhibits oxygen isotope excursions in the opposite direction of Ernest Henry and towards meteoric water and seawater. And so from this, we can infer that there was a significant meteoric or other surface water component in the mineralizing fluids at Osborne, which has not been demonstrated with triple oxygen isotopes at any other iron oxide apatite or iron oxide copper gold deposit. So this is pretty interesting, again, also because it's a very cut and dry mixing line between magmatic origin or potentially even metasedimentary input. It's really hard to pull this apart because that's sort of on the opposite side of the meteoric water, and so it could just be in the magmatic origin range sort of by chance because you're mixing two things on either side of the magmatic origin range. But nevertheless, this is very interesting, again, because it's so different from Ernest Henry, which is in the same district. To summarize, the stable isotopes have been very informative as to the metal and fluid sources. So at Ernest Henry, we can see that the oxygen was from magmatic fluids or potentially fluids that equilibrated with igneous rocks, whereas the iron was leached from crustal rocks, and that had never been observed in an iron oxide copper gold deposit before using metal stable isotopes. Whereas at Osborne, it's a completely different story. So the oxygen was from a mixture of meteoric water with either magmatic or metasedimentary fluids, whereas the iron was not leached. It was largely from the banded iron formation host rock, and the iron isotopes do seem to confirm that the protolith was a proper banded iron formation. And so, in addition to the really diverse mineralogy and physical characteristics of the Cloncurry IOCG deposits, they also have a pretty diverse metallogeny and fluid origin. And this suggests that the IOCGs, particularly in this district, are related by something broader than the exact geodynamic setting or metal and fluid sources, and that it's really more of a process thing that they have in common. But of course, this remains to be explored by continuing to test the other really diverse deposits in the Cloncurry District. So thank you for your time. I apologize I can't be there because of a time zone conflict, but I really appreciate the opportunity to present my research in this forum. Thank you for listening.
So I'd like to thank Chris for that presentation. If there are any questions for Chris, you can reach him via email. So you could send that directly to Chris, or you could email the GSQ, and we're happy to forward that email through to Chris if you have any questions for him or you want to discuss some of his research. Our next speaker is Xin from the University of Queensland. Xin is going to talk about Garnet geochemistry for fingerprinting of mineralization processes in the Mount Garnet zinc deposit in northeast Queensland. Xin, if you would like to share your presentation and start off, please.
Thanks, Beth. I will share my screen right now. Good afternoon, everyone. My name is Xin Wang, and I'm currently working as research assistant at University of Queensland. Today, I'm going to talk about my honors project with the title of Garnet Geochemistry for Fingerprinting of Mineralization Process, the Mount Garnet Zinc Deposit, Northeast Queensland, Australia. So this project is collaborated with Geological Survey of Queensland and under the supervision of Dr. Ranger Zhou from EQ and Dr. Alina Belosova from GSQ. Here's an overview of my talk, starting from the background information case study to the conclusion. So first thing first, please see the right side image where a bunch of garnet crystals are shown here. So what is garnet? Garnets are a group of silicon minerals that are commonly found in hydrothermal system. And from the graph down here, you can see that there are a variety of different types of garnet, and each has a different chemical composition. This wide variation in geochemistry determines many of their physical properties and reflects the change in local environment. Therefore, garnet is often used as an indicator mineral for geological assessments. More about Northeast Queensland, why I was so interested about this area. The answer is that it hosts many critical mineral deposits, as you can tell from the map here. This region covers a lot of important mineral commodities, such as zinc, lead, gold, silver, tin, tungsten, and many others. The unique tectonic setting of this area allows the development of different types of mineral systems, where the subduction process leads to the regional magmatic activities and the occurrence of granite-associated mineral deposits, such as skarn, as demonstrated in the model here. Over the years, researchers had focused on individual deposits within this area and found out that they are very complex and have distinct features. So dive deep into my study area. Mount Garnet is located in the central eastern part of northeast Queensland, and is considered as one of the most important areas for skarn deposits. These skarns are hosted in granite intruded sediment rocks, namely the Chibuzo Formation, colored as purple on the map. Two types of skarn are displayed in this area. One is dominated by fluorine, tin, and tungsten, such as the pinnacle tin perspective on the top. And the other one is zinc dominated, such as the Mount Garnet zinc mine in the middle. As I mentioned before, the skarn formation is driven by magmatic activities and highly associated with large igneous province in northeast Queensland. So this province contains three major supersuites that are listed in the table, where you can see that the O'Brien's Creek supersuite being the oldest and the most reduced igneous unit, as well as the most chemical involved one, where the Claret Creek being the least. For many years, the main research question around this area is that which igneous unit should be responsible for different skarn formations. Two hypotheses had been evoked by Askins and Brown with his colleagues, that either the oldest O'Brien's Creek or the youngest Claret Creek have resulted these skarn formations. So in this study, we were testing out these hypotheses by taking detailed mineralogical, geochemical, and geochronological analysis on skarn samples that taken from the site. So a total of 7 representative samples were given by GSQ. Thanks Connie and Fred from GSQ for providing these samples. And 4 of them are from Mount zinc and the rest from pinnacle tin. In addition, 9 sections and 18 rock mounts were made out of this scan sample for detailed study. We also use 3 different petrographic techniques, including the traditional method and a more advanced method, such as SEM and TMA. 2 more methods, including EPMA and laser ICP-MS, were used for major trace element analysis and uranium-lead dating on garnets. So based on the result, different types of garnets were identified. As you can see from the image A to D, that the garnet 1 has a very regular shape under the microscope, and showing in green, yellow to pinkish color, as well as a zoned pattern in the BSC image here you can see, where the core is classified as 1A and the ring is classified as 1B. On the other hand, Garnet 2 has no zoning pattern shown, displayed a very massive habit and a light brown color as seen from the image E to G. TMA mineral phase map on the top right side have also confirmed these observations. In addition to different characteristics of these garnets themselves, they are also associated with different ore minerals. As you can see from the left side BSE image, the garnet 1 is highly linked with some sulfides, such as chalcopyrite and sphalerite. Whereas the garnet 2 is more related to tin and tungsten bearing minerals, such as cassiterite and scheelite, which you can tell from here. Remember the garnet graph I showed at the beginning? Different garnets have different chemical composition. So in this study, garnet 1 in this plot has similar major element content as garnet 2, and mainly contains the crucial aluminium-rich garnet, whereas the garnet B is more andesite dominated. The change in concentration also shown in figure B and C, where the aluminium content in zoned garnet specifically decreasing from the core to the ring, and the iron shows the opposite. As for the trace element, apparently all these garnets contain a high amount of tin and tungsten. However, their rare earth element trends are very different. Garnet 1A tend to have more heavy rare earths than light rare earths, and which is quite similar to Garnet 2, but it has a weak positive European anomaly in comparison. The Garnet 1b is light rare earth enriched and heavy rare earth depleted with strong positive European anomaly. More importantly, Garnet 1b has a very suitable uranium-lead ratio, so we managed to do a uranium-lead date on this type of garnet. Just in case you might confused with all these garnets, here's some figures that tells you what IB looks, Garnet 1b looks like. So the uranium-lead age of this type of garnet is around 296 million years plus or minus 1.7 within 2 sigma error. Combine all the information we collect for this garnet, the evolution of garnet formation and the change in fluid activities can be revealed. From the model I draw here, you can see Garnet 1 is likely to be formed first at the prograde stage where you have less amount of magmatic fluid coming out. And the Garnet 1b are more likely formed at the peak metamorphism with increasing temperature condition and high water rock ratio. This large volume of fluids carries a lot of metallic elements, and shortly the sulfate deposition happened. The forming condition for Garnet 2 is a bit tricky, where it is formed after or before the zoned garnets are hard to define. Although the texture of these garnets and the close relationship with hydrous minerals such as chloride tells that it could form in an open system and might undergo extreme hydrothermal alterations, which can happen at a later retrograde stage. As they can be seen, and also they can be seen with these fluorine, tin, and tungsten veins, which tells us they are likely formed in a mixed fluid condition with a different fluid source, where high fluorine activities are displayed. Based on these characteristics and the geological correlation of the igneous units, the fluid source for Garnet 2 are likely to be the O'Brien's Creek. Due to the similar geochemical characteristics where you have more reduced, more fractionated, high silicon, aluminium, fluorine, tin, and tungsten content. As for the Garnet 1b, the youngest Clarish Creek supersuite might be responsible for its formation due to the similar age range, which is around 300 million years, and the similar chemical properties. So a little bit summary for today. Diverse types of garnets are identified, and their relationships with mineralization is also discovered in the Mount Garnet skarn deposit. New geochemical and geochronologic data allows us to test the hypothesis regarding the igneous source and fluid evolution. For future research direction, we can do more systematic characterization on garnets and other major hydrothermal minerals such as calcite and fluorite to help reveal the regional magmatic activities. And that's all for today. Thank you very much for your time.
Thank you very much for that, Xin. We do have time for a quick question. So if you are online, you can raise your hand using the button at the bottom of the screen, and I can elevate you to ask the question. Otherwise, you can type it into the Q&A box. So do we have any questions for Xin? Looks like you got out of that one easily. Xin, we'll move it along. So if you think of something, we'll have a quick Q&A session at the end as well. So moving along now to Alanis Olesch-Byrne. Alanis is a PhD candidate at James Cook University, and she will be presenting on the structural controls on ore deposit genesis for the Mary Kathleen rare earth uranium mine, uranium deposit in northwest Queensland. Take it away.
How does that look? Can you see my screen? Perfect.
It's
All right. Hello everyone. Thanks for coming along to the webinar
wait a
series.
second, Alanis, we've got the wrong screen.
Oh,
Yeah, we've got the your presenter screen, so you can use this.
there we go. Is that better?
Perfect.
Okay, cool. Awesome. Sorry about that. I did get it right beforehand. I just obviously didn't get it right this time. Cool. So good afternoon, everyone. My name is Alanis Olesch-Byrne, and I am a PhD candidate at James Cook University. And today I'll be talking a little bit about my PhD project. I want to begin by acknowledging the Bindal people who've been caring for the region known as Townsville for many generations, and the traditional owners of the land in which I conduct my research, so the Mitakudi, Kalkadoon, and Pita Pita peoples. And I recognise their continuing connection to the land, and I pay my respects to their elders, past, present, and emerging, and extend this to all Aboriginal and Torres Strait Islander peoples. So a little bit of an outline. So I'm going to do something a bit different. So I'm actually not going to talk about heaps of geochemistry work or dating or anything like that. I'm actually going to be talking about field observations and because I think that field observations are really, really important, and you know, understanding the lithologies of the outcropping geology gives a lot of context to the underlying geology, and you know, why certain ore deposits form, and you know, why they form in a certain place. So I'll be talking about my field observations, talking about protolith and also some deformational controls, and also a little bit of future work with GSQ. So I wanted to start off by talking about rare earth elements. You know, that one of the most important ore deposits for the future is that of rare earth elements. So why do we care about them? Why exactly are they important? The rare earth elements consist of 15 lanthanide elements plus scandium and yttrium. While rare earth elements are abundant in the Earth's crust, their occurrence in economic quantities is not very common, hence the term rare, and especially hard rock rare earth element deposits like Mary Kathleen. The global demand for rare earth elements has consistently increased over recent decades as these elements have become more important to modern life, and rare earth elements get used in renewable technologies such as wind turbines and solar panels, electric cars, and also consumer electronics like computers and your smartphone. So to provide a little bit of context of my field area, I work within the Mount Isa Inlier, specifically within the Mary Kathleen domain. So this is a map of all of the all of the prospects, current operational mines, and legacy mines of Queensland. And the Mount Isa Inlier is in northwest Queensland, and it features a lot of copper, gold, rare earth element, and critical metal deposits that are of significant economic importance to Australia. So the Mary Kathleen uranium and rare earth element deposit is a previously open cut pit, which makes studying the deposit and its surrounding structures and lithologies perfect, and is also the main focus for my PhD. So what exactly do we know about the deposit? We know that according to the literature, the age of the deposit is around 1550 plus or minus 15 million years, according to uranium-lead dating of uraninite, which is thought to have defined the actual ore deposition. The ore deposition occurs as veins of garnet and uranium and rare earth element bearing allanite. The uraninite ore is found as fine disseminations enclosed within the allanite grains. So I just wanted to touch on the Mary Kathleen shear zone quickly, since I'm a structural geologist and I think shear zones are the coolest thing ever. Many hydrothermal ore deposits actually occur adjacent to ductile shear zones, suggesting that their role in ore deposit genesis should be probably looked into maybe in a little bit more detail than they currently are. The Mary Kathleen uranium and rare earth element deposit, for the purpose of my study, shows both the deposit, which is here in blue, and let me put my pointer on. So here in blue, and then the yellow here is the shear zone. So the open cut pit shows both of those outcropping beautifully. So the Mary Kathleen shear zone, according to the literature, is roughly 30 to 50 meters in diameter, dips steeply and runs parallel to the axial trace of the Mary Kathleen syncline, which you can see really roughly here in your image to the left. It's also another important thing to note is the Elaine Dorothy prospects here towards the south. It also runs along the shear zone, which suggests that maybe the Mary Kathleen shear zone is a major shear zone in the region with really significant regional implications. All right, so I'm going to start off with some field relationships. So I'm going to specifically start looking at the protolith of the ore deposit itself. So by looking to the north and to the south, so the north up here of the deposit and to the south of the deposit, we can start to understand what the rocks were before the ore deposit formed. As I'm sure a lot of you know, the Mount Isa region has experienced a lot of different hydrothermal events, which sometimes makes determining the protolith quite difficult. So to the north and to the south of Mary K, we can actually see a repeated sequence. So really roughly schematically, I've overlain that on this map here. And we see a repeating structure of the Corella Formation and amphibolite. So the Corella Formation is here in pink and the amphibolite is here in black. And we also see then the Corella Formation outcropping again to the west of the amphibolite. This gives us some idea of what the protolith of the deposit was. Probably not the protolith before it was altered. It has undergone a lot of alteration, but it does provide a little bit of context. All right, so both of these two protoliths experienced variable K feldspar alteration. All right, so within the Corella Formation, we can see partial potassic alteration that expresses as cross-cutting K feldspar veins. So you can see that here, so cross-cutting K feldspar veins. And within the adjacent amphibolite, we can see that the potassic alteration is far more pervasive. And basically the amphibolite has been completely overprinted and replaced by K feldspar, as seen here in this image. The really pervasive K feldspar alteration occurs in and around the pit, and you can see variable K feldspar alteration occurring to the north and to the south of the deposit itself. So this here is an image. I'm sorry, it's a little bit dull, but you can see in this image here, so this is facing the north and I'm on one of the southern walls of the deposit. From this image, you can see a light colored lithology here tracking along through the middle of the image. This is a non-continuous layer. So this is so from a bird's eye view, what that layer looks like. This is a non-continuous layer of calcite that does not extend to the north or to the south of the deposit. The calcite is actually at the boundary between the calc-silicate, so the Corella Formation, and the amphibolite. This is important as it is a really distinguishing feature of the ore deposit itself, and it could hold the key into understanding why the deposit has formed here and not anywhere else, because we don't see this marble expressing anywhere else within close proximity to the ore deposit. So this is a schematic image of the previous slide. So as a cross-cut, as a cross-sectional view through the deposit itself. So this calcite unit we refer to as a marble myelinite, and in the literature it's also referred to as the Mary Kathleen shear zone. So the Mary Kathleen shear zone shows west block up movement, which according to Nick Oliver in 1991 caused the displacement of around 2 kilometers, which is thought to have uplifted the Wonga belt. Structural measurements show dip direction of basically north-south, 0 to 180, and a down dip stretching lineation, which is defined by biotite, and it plunges really steeply around 85 to 90 degrees. The most important takeaway from this is that the Mary Kathleen shear zone is considered to be a very significant shear zone in the region if it's causing 2 kilometers of uplift. But the extent of the shear zone, as well as its place within the regional context, is not well known, and it requires a lot of further investigation. All right, so again, this is the cross-sectional view. So what I want to try and show you is that there's a really large competency contrast between the calcite, so the marble myelinite, and the massive K feldspar alteration of the amphibolite. The calcite, as you can see here, is very weak, and it is an area of high strain, and it is experiencing ductile deformation. The K feldspar altered amphibolite, on the other hand, is very competent, and it's probably at the time of this specific cross-section wasn't undergoing any deformation. While it wouldn't be deforming, it's probably experiencing very high stress because of the very high strain in the adjacent weak marble myelinite. This could have led to the possible fluid buildup on the margin between the marble myelinite and the K feldspar altered amphibolite. So the stress in the potassic altered amphibolite basically will eventually exceed the strength of the rock, which will then cause brecciation. So this brecciation and fracturing introduces fluids into the K feldspar altered amphibolite, and this alteration occurs along the fractures in the competent potassic altered amphibolite, and basically through fluid ingress, and depending on what the fluid is, we see alteration. The fluid in this particular context is thought to have been the first major skarn event. So basically bringing in a garnet matrix. So we can see here in these two images, so we've got a larger scale and a smaller scale. We've got the breccia blocks of the K feldspar with garnet matrix around the brecciated competent K feldspar. This then leads on to ore formation. All right, so an important note for that is that the ore only occurs within the skarn, and the scar does not occur on the western side. So over here, there's no skarn and there's no ore on the western side of the shear zone here. The veins actually cross-cut the skarn and therefore indicate that it probably occurred post-skarn formation. There are a few different options to explain why the ore veins have formed here. And I have some preliminary geochemistry work, so I will hypothesize to one option, but there are many options. So yeah, and a lot more work is actually required to fully understand it and understand the regional context of the ore deposit itself. So the preliminary geochemistry of the garnets are that they are highly enriched in uranium and rare earth elements. And we hypothesize that the skarn was probably enriched in the uranium and rare earth elements, which was introduced when we brecciated the K feldspar. And then this was basically reconcentrated into brittle ore veins like that you can see here, that through a later metasomatic event, which then cross-cuts the skarn and is forming these allanite and uraninite veins. So that's just a little bit of, I guess, field relationships and like really important information that we can tell from relationships that we can see in the field. You'll also notice that I didn't mention the regional geology of Mary K, and this is for a good reason, because we don't yet fully understand the actual regional geology. There's a lot of dispute about, you know, certain deformation events, and we're trying to figure out a model for ore deposit genesis without the influence of previous models on our particular model. So future work, we actually are doing a ground gravity survey with a grant from the Australian Society of Economic Geophysicists. That's starting in a couple of weeks, so on the 18th of September. And with that, we're going to try and see if we can follow this amphibolite package to the north and south of the deposit. We're also doing detailed petrographic work on the garnets and on different metasomatic minerals within the deposit to really get a handle on the paragenesis of the deposit. And once we've got a handle on the paragenesis, we'll be doing detailed in situ dating of the garnets and allanites with Courtney and Eleanor from GSQ to really get an idea of, you know, we've got a lot of people have dated the garnets from the deposit, but this way we'll actually get an idea of what we're dating and through those different relationships, get some more understanding of what those ages actually mean. We're doing some oxygen isotopes at Curtin University, so that will be pretty exciting to get some sort of idea on possible sources. And we're also conducting EBSD on the marble myelinite to get an idea of the different deformation mechanisms that occur within the marble myelinite. So thank you so much. Does anyone have any questions?
Thank you very much for that, Alanis. Fascinating. Yeah, once again, if you do have a question, please just raise your hand in the chat or type it into the Q&A box. Or save it up for later. I do have some questions about that because I really like that area, but I'll save it up after because I don't want to hog. John Menzies, we have a question. Go ahead, John.
Yeah, hi, just showing my ignorance. What does EBSD mean?
So basically what we're doing is we're having a look at the orientation of different grains within the myelinite, and we basically from that we can tell what kind of deformation mechanisms are occurring, so whether or not they're going through dissolution precipitation, and whether or not we can see pure shear or simple shear that's occurring within the shear zone. So it's really mapping out each grain and getting the orientation of each grain to give us some better understanding of the deformation mechanisms.
Outstanding, thank you.
Oh, good.
We also have a question. Questions come in from Emma Beattie from the survey. Can you see that one there, Alanis? I'll just read it out in case anyone can't see it. But are you in touch with the explorers who have tenure in the area? I reckon they'd be really interested in the gravity survey. And yes, this was one of the things I had written down from some later questions as well.
Yes, I am in contact with a few of the companies within the area, and we will be collaborating. So they've also got a lot of some really nice high detailed and high quality maps of the area as well. It's a little bit disjointed, so within the area people focus on their own tenements, so hopefully this will link a couple of the tenements together, and it will kind of focus on a lot of different prospects within the syncline itself. So yes, no, it should be really great, and I'm very excited to see what the results are.
So, when I was working for Chinalco years ago, we did a detailed gravity survey across the whole syncline, and it picks out the Garnet skarns amazingly well.
Yeah.
Models all them up, that density contrast comes out very clearly.
That's what I want, so that's good.
And that should all be on the GSQ, on the open data portal as well. You need that data. Very good. Well, if that is all the questions for us, we thank you very much for that fascinating talk. I'll move on now to Chibuzo Chukwu, who is a PhD candidate from Monash, and he will be talking about a new approach to imaging crustal structures using machine learning on geophysical data. Please welcome Chibuzo.
Yeah, thank you. I would like to share my screen, don't mind. Is that coming out well? Just to be sure.
Yep, you're good to go.
Yeah. I'll be sharing, I'm a PhD student here in Monash, as mentioned, and I'll be sharing with you part of my PhD that has resulted to a new approach in imaging structures using machine learning on geophysical data. I pay my respect to the Queensland Nation, which are the traditional owners of the land where I conduct my research here in Monash, and I pay my respect to their elders past and present. The two major phrases that stands out in my presentation is machine learning and geophysical data. And I would show you, and there are two major motivations to this presentation, and of course the research. One is the current trend and attention given to machine learning, and this is because machine learning enables us to identify major trends and identify ambiguities in our geophysical data. And from what you can see from the map, from the bar charts, let's go to get my pointer up. This is a database of the SCG, which is one of the most published geophysical data and as well papers in the world. And you can see the growth in application of machine learning to geophysics, geophysical data. But particularly if you look at the methods, you would realize that this attention has only been drawn to seismic, but not other geophysical methods. Particularly, little attention has been paid to gravity and magnetics. The second motivation is actually to image structures beneath volcanic fields, lava fields, essentially. Here, we try to show how this could image structures beneath the newer volcanic province, which is southwest of Victoria. But for the geologic context of southeast of Victoria and the area I'm talking about is that it has majorly three blocks, which we refer to as the Delamerian Fold Belt, the Lackland Fold Belt, and a microcontinent, a Neoproterozoic microcontinent that accredited to South Victoria, resulting to these majorly north-south structures. The challenge is actually, we know what these structures are in Victoria, central Victoria, but as it goes beneath this newer volcanic province, which are Paleocene in age, we can't image these structures, even in seismic, gravity, and in conventional magnetic data. For our study, we actually started with a global magnetic data, and that's for some reason, we had to use a global magnetic data, which is the EMAG. This global magnetic data has low resolution, and it gave us a bare eye view how this method could work. We tested our results using seismic interpretation and gravity modeling south of the newer volcanic province, where we could actually see the structures of this data. And I'll also show you how this method had also worked in high resolution magnetic data and the relevance of this study to Queensland. Our method depends solely on the popularly known Euler deconvolution method. And for some explanation, the Euler deconvolution method works on this equation using ensembles of magnetic points or data to resolve structures based on what we refer to as the spectral index. For the spectral index gives or allows us to tweak the dimension of the depth of magnetic anomaly calculated using this method. So if you use a spectral index of 0, you get to calculate one dimension of the structure. If you're using 1, you get to calculate 2 dimensions of the structure, especially for magnetic data. What you can see is results for n equal to 0 and n equal to 1. And what we realize is that the Euler results produce results, calculate depth values for edges of structures, on edges of structures when n is equal to 0. But when the spectral or structural index is equal to 1, it produces results for both the edge of the structure and the plane of the structure. So you would expect more depth results for n equal to 1. Now, this gave us a clue that the results could also be produced within and beneath the newer volcanic province because these values are quite high for n equal to 1. So we pushed that further using machine learning to cluster cross sections of these depth results. We took 2 cross sections. One is as a control, which is taken near a pre-interpreted seismic line in Victoria, and the second actually across the newer volcanic province. As you could see, the cross sections produce no geologic information when they are not clustered yet. So then we now use the DB-scan, which is an unsupervised machine learning algorithm to cluster these cross sections. This is the result. A is the result when clustered. And what we realized is that these clusters, the edges of these clusters perfectly align to where these structures are. As you can see at the middle B, you see that these structures, the boundaries of these clusters actually align 1-to-1 to the pre-interpreted seismic line. Secondly, you could also see that these boundaries also respect the cross-cutting relationship of these structures as previously identified, even at deeper depths of 30 kilometers. Now, this gives us clue for 2 things. One is that some of these structures actually cross beneath the Paleocene basaltic rocks of the newer volcanic province, and 2, they've gone beyond the newer volcanic province and possibly into Ottaway Basin, into beneath the sediments of Ottaway Basin. So what you see now is the cross-section across BB prime. And what you realize that the cross-cutting relationship still persists beneath the newer volcanic province, which is actually the first time these structures are imaged beneath basaltic province, and particularly here in Victoria. So when we've identified this, we now felt to test the extensions of these structures beneath south of the newer volcanic province. And the first thing we did is to choose one of the beautiful 2D deep seismic line to see if there are cross-cutting relationships and the architecture of these structures persist. And this is what you could find for this seismic line with 04023C. And what you see is that these structures still persist beyond the newer volcanic province, south of the newer volcanic province. So we pushed it further using another seismic line, the famous 13709, to see if we could actually test our interpretation using gravity model. And we used this line to constrain our gravity model. But before you could do that, you have to convert the two-way time seismic line into depth. And to do so, you need a velocity model. What you see on the right are the inputs to the velocity model that allows us to constrain both the horizon and the depth of our interpretation, of our seismic interpretation. And what you see is the velocity model constrained from top to the borehole. When you apply this velocity model to the two-way time, you get the section in depth, and this can be easily modeled. When you model it, knowing the petrophysical characteristics of the rocks, you can easily model this, and what you can see is a well-constrained gravity model across one of the major faults. And what we realize is that not only these structures are developed in the Cambrian, but they still control the breakup of Australia from Antarctica, and even the basin development, part of the basin development of Ottawa Basin. The question everyone would ask is, are these applicable to everyday high-resolution magnetic data set? And to test this, we applied it in a location. We know what the structures are in central Victoria to test how good this approach is. And luckily for us, or would I say fortunate, it works because it's able to identify the architecture of known structures in central Victoria. How could this be applied in Queensland? We are aware that Queensland covered more than 1/3 of the lava field and central shield volcanoes in Australia. And if it worked for the newer volcanic province, we believe it can also work in Queensland, especially where, especially the Mag Bridge. If you look at the magnetic data, you would see that the magnetic data does not give fabric of basement structures that you can easily identify south and north of the Mag Bridge volcanic province. So the solution could be our approach, and we believe that when our approach is applied to this area and other volcanic areas, not just in Queensland, but around the world, we'll be able to have the architecture of these structures even beneath or across the volcanic province. We are currently extending this project to other geophysical data sets like magnetics and MT, and hopefully in the near future, we'll be able to demonstrate it also works. Thanks to my collaborators and institutions that have supported this research. Thank you.
Thank you very much, Chibuzo. Fascinating talk. Do we have any questions for Chibuzo? We have time for a quick one. Yes, we have time for some questions.
Well, while people are looking for questions themselves, I just want to say thank you. That was a great presentation. I really liked your forward modeling of the gravity offshore. That was spectacular, the fit you were able to achieve with the seismic there. And just for your information as well, we're currently flying a magnetic survey right near Ondara right now. The planes are in the air at the moment. So we should have some new data in the next couple of months over there. So we'll have some new very high resolution data that you better use. But I'm very interested to see the application of some of those works to look under those basalts and understand those structures. And if you haven't already, talked to David Purdy at the Geological Survey of Queensland, who's doing work on those volcanics on the eastern coast. There's lots of interest in the peralkaline volcanic units, but also some of those basalts along the east coast. So yeah, terrific, great presentation. Really enjoyed it. Don't have a question for you, but I'm really enjoyed it. Thank you.
We've seen very promising results in Antarctica as well, because we're also trying to find the tectonic connection between these structures and their mirror images in Antarctica, and the results are quite outstanding already.
Great. Do we have any other questions or comments? Sorry, it wasn't really a question. It was just a acknowledgement of what I think was a great piece of work.
Okay.
If not, we might keep going. So our next presentation is Tian, from the University of Queensland. And her presentation is titled "How Cumulate is Your Whole Rock." Thank you, Tian.
Yeah, I'm from QUT. Yeah, sorry, not your QUT.
Sorry, pardon me, QUT.
I'm going to share my screen and so good afternoon, everyone. I'm Tian from QUT, and I'm because Lisa, she is not available today to give a talk, so actually I'm take up her. So today I'm going to give a talk about my PhD project. It is how cumulate it is your whole rock. So first, I'm going to acknowledge the traditional owner of the land where QUT now stands. Then I'm going to just quickly give a brief of my the background of my talk. So it is part of my PhD project called the trace elements fingerprint in accessory minerals. They are zircon, apatite, and titanite, and can they assist in finding gold deposits? This project is supported by ERC linkage grant, and it is mainly focused on the study of potassium-rich magnetic system. So this linkage project, actually, it is collaborate with 3 universities. They are UWA, NU, and QUT. So from the title of my research, you can see actually it is a igneous petrology study, and I'm mainly focused on to study the equilibrium relationship among these 3 minerals. So the first questions, it is, what do people use whole rock geochemistry for? So when you go into the field and you grab a rock, and the rock it is in the front of you, and you want to know something from that rock. So we want to know the magma evolution and how all the melt or crystal evolution. We want to know some essential information, for example, like temperature, pressure, and also the melt composition. The problem is, how can we calculate them, especially for the melt composition? So usually we will use some models based on the mineral compositions or the mineral assemblage. So for example, we use accessory minerals. One of the most well-applied models, it is the zircon saturation temperature, which is studied by the Harrison and Watson in 1984, although it is, 30-ish years ago, it is still, people still use this equation. So from this equation, you can see, if you want to know the temperature of the magma, you need to know what's the distribution coefficient. If you want to know the distribution coefficient, you want to know how much zircon actually is, how much zirconium it is in the melt, and how much zirconium it is in the zircon. So we also need to know what is the M. It is the melt composition parameters. It is also representing a factor reflecting the melt composition. Therefore, you can see we have 2 assumptions. First, you will use the whole rock composition to represent the melt composition. Secondly, the mineral you select to calculate the pressure, temperature, or the melt composition, you need to be equilibrium with the whole rock or the melt. But there has some problem, very obvious problem. First, it is the saturation temperature. It is not actually the crystallization temperature. Saturation temperature, it is the maximum temperature of the minerals such as zircon, which the beginning of occurrence. Usually it is the maximum temperature, it is higher than the actual crystallization temperature. Secondly, the whole rock composition, actually it is different with the melt composition. And if your rock has something like a xenocrystallite or heritage minerals, your whole rock composition, actually it is different with the melt composition when it was formed. So another problem, it is for the plutonic rock. Because during the very long time period of cooling, the melt can be lost, or the crystal can be accumulations. That is same things. So therefore, if your melt, it is not equal to the whole rock composition, then you calculate with the wrong M. Then with the wrong distribution coefficient, you can get a wrong age and wrong temperature. Therefore, there are some other models they can try to figure out. For example, there's titanium in zircon thermometers. It is also developed by Watson, but is in 2006. This is another one of the most applied and reliable model to estimate temperature. So you only need titanium concentration in zircon. You don't need anything else. But the problem is, if the select mineral, it is not in equilibrium with the melt. For example, it probably formed in the very beginning stage or very late stage. So which means they are can't be represent the whole event. So in my study, we introduced a new concept. We call that equilibrium container. So from this photo, actually you can see here, it looks like a container. So we select amphibole, because one reason, it is one of the most common major mineral. Secondly, amphibole, so therefore you can see amphibole in most of the igneous rock. Sometimes I explain to my friends what is equilibrium containers looks like. Explain to them, it looks like a bubble tea. the accessory minerals, like the bubbles in the bubble tea. So to identify how to make sure those accessory minerals, they are in equilibrium with amphibole, we have two we need to say they must be physical contact, or they need to be composition in equilibrium. For example, you can see the elements has been, there's competitions for the elements between two phases. Another reason to select amphibole, it is because amphibole itself can be used to estimate melt composition. They have, for example, the Zhang et al. 2017 model and also R&R 2012 model. They are two very most applied model to estimate melt composition. So now we want to test how good the model it is. So first we use the P-string tooth as an example, because we all know the volcanic rocks, they are quite different with the plutonic rock because they doesn't have accumulation problem. So we assume the result from P-string tooth probably will be very similar with the melt composition probably will be really similar with the whole rock composition. So, and also the temperature temperature from the literature, calculate based on the zirconium in titanite thermometers. It is around 769 plus minus 20, and calculated by the zircon saturation temperature, it is 770 to 780. So actually they grade very well to each other. So then I did the microprobe work and on the amphibole, and I plug all of my data into the Zhang et al. 2017 data. So 2017 models to calculate what is the estimate melt composition. So now from the result, we see this is a 1-to-1 line. The calculate melt silica contact, it is around 72, 74, 76. It is very close to the literature whole rock silica contact. That's a really good news because, which means the model developed by Zhang et al. 2017 it is working, and it is working. So now we want to use this model to test how plutonic rock. We use the rock from the Turtle Pluton from California. So they give us a very, very big different result. The calculate melt silica contact, it is also around 74, 76, 78. But the whole rock silica contact, it is around 64, 68, which means there are almost like 10% difference. And also that I want to know what is temperature or pressure. I put my data into Paterka's 2016 model. It is also another very well applied model. You can see if I put my data into the whole rock, I use the whole rock chemistry data to calculate the temperature pressure. It sits around 930 degrees C. It completely doesn't make sense for plutonic rock. Plutonic rock, you can't reach to that temperature. But if you use the calculate melt composition to calculate the temperature and pressure, it sits around 780 degrees C. Actually, that makes more sense. So therefore, in summary, especially for the plutonic rock, melt loss or crystal accumulation can make a very big difference in melt composition than the whole rock composition. Therefore, when you use the whole rock composition to represent the melt, probably need more careful to consider it, and probably you need to think about to use a chemistry to check how cumulate your whole rock might be. Thank you very much.
Thank you very much, Jan. Do you have any questions from the audience? If you want to raise your hand, we can allow you to speak, or you can ask them in the Q&A or the chat box. Just give a couple of seconds in case there's anyone who has a burning question. If anyone has any follow-up questions to any of our presenters today, I'm sure everyone will be happy to receive an email or contact after that. And if you do want to contact any of our presenters today and you don't have their details, please contact Evan or anyone at the GSQ, and we're happy to forward those through to you as well. So our next presentation is from Yifei, and I hope I pronounced that correctly, from the University of Queensland, whose presentation title is to understand, study, and characterise current and known problems with risk management practices using causal network topology analysis.
Thank you. Thank you, Greenwood. I'll share my screen.
Please do. Yes, it's working. Thank you.
Am I sharing? Yes.
Yep, that's great.
Okay. So hello everyone. I'll describe my thesis. Okay. So I'll start with some background. In the discipline of risk management, there are various classic incidents involved multiple inherent causes. Let's look at some key examples. In 1986, the Chernobyl nuclear power station accident, a reactor failed to shut down when needed. The design didn't account for the increase in reactivity caused by the protection rod's insertion. In 2011, the Fukushima power plant accident, the tsunami disabled the diesel generators intended to cool the reactors. Risk management failed to consider the interconnected nature of risks. In 2018, the 737 MAX incident, new software designed to prevent the plane from stalling, however, conflict with pilot control, showing that mitigating one risk can create another. These three examples highlight accidents due to a lack of insight into causal context. In 2012, within my company, a software update went wrong, costing millions. The risk was not managed across different departments, showing a lack of organizational context integration. In 2017, a fire occurred at the Grenfell Tower. One of the causes due to the cost cutting led to the use of flammable materials, illustrating the dangers of lack of integration of organizational context as well between the financial department and the safety department. Challenger explosion and the explosion occurred at BP Texas City. Both disasters were partly due to the poor data integration. Important information was discussed, but not formally recorded or integrated into decision-making. And the final two, Deepwater Horizon and Ocean Gorge accident, in both cases, stakeholders had different perspectives on risk, but failed to integrate in these views, leading to unwanted outcomes. From what could be observed by all these accidents, there clearly was a history of a lack of integration of context among the causal, organizational, data sources, or stakeholders embedded as potential causes to those accidents. There was also an issue of a lack of integration of those contexts, which has been long claimed in the process of risk management. In risk management, to ensure the contexts are well integrated is an important part. However, it's challenging. First of all, risks themselves are split up and managed separately during the risk optimization process. Secondly, the scope of the risk assessment is split up within one organization because of organizational silo. Risk information is also split up into different information formats, making it hard to integrate data source contexts. For example, spreadsheets are typically used for capturing risk registers, HAZOP or FMEA, and written documents often hold incident reports. And finally, the perspectives of stakeholders are split up. Diverse stakeholders perform subjectivity while doing their decision makings. However, these stakeholders do not always have the same perspectives on what the goals of the systems are, what the risks are, nor how to treat them. Remember the past accidents which were related to the failures of large infrastructures, systems, or operations. They were often caused by inadequate decisions made by the decision makers. The quality of these decisions made by the decision makers are highly depending on the uncertainties in the information received by those people. from what have been learned by studying past accidents, there should be a link between the lack of integration of context and the uncertainties in the information received by the decision makers. These information could be the risk data, which has the results from the risk management process. And for the background introduction, finally, I'm going to introduce some of the common uncertainties embedded during the risk management process. First of all, guidelines ISO 31000 indicates the initial step of risk management is to identify the scope, context, and criteria. To select an appropriate set of risk methods to characterize the system and the scope is important. However, the decision on making selection is based on experiences, which is sometimes subjective and may cause uncertainties. There are also uncertainties during the risk identification process. Risk analysis describe events at various granularity levels, which is related to the level of detail used in describing their risk identification data. This is often due to the different goals of doing risk management, and the differences in granularity can cause uncertainties. And finally, risk identification data could be incomplete, which is often due to the misidentifying all the potential risks. So my research is focusing on multiple sources of uncertainty, which has been described in the previous slide in the risk management process, with the development and application of a graph-based tool as the research method to understand, study, and characterize those uncertainties, and finally, to review the relationships between the sources of uncertainties and the lack of integration issues, which I have mentioned in the beginning. So why choose a graph-based research method? This is because graph-based tools have been used for years to capture properties of a complex system or scenarios for better understanding. And also, as mentioned in ISO 31000, to understand and examine the context, need to include the complexity of networks and interconnections, which graph-based tools are well suited. Considering a connected graph with nodes and edges and named as a network, according to past literatures, those network analysis has been applied widely in risk management discipline to reflect the properties of a complex system of scenarios and the information derived from the network structure, which is called network topology, will inform more insights to risk analysts. I will provide a simple network topology results. The network matrix are the measures reflecting network properties. For example, degree means the number of edges linked on one node, and betweenness calculates times of one node locates on the shortest path between two other nodes within the network. The implication of using such individual measurements was to represent the significance of one risk or the cause in the system. My research takes advantage of from gaps indicated from past literatures, which has applied such network topology analysis to manage risks. That will be the sensitivities of the network analysis method itself. For example, while describing a same event, different authors tend to describe that event differently. One author might describe a risk event in one sentence and convert that one risk into one node in the network. The other might separate that risk event into two different risk events for a more detailed description. However, this will result in complete different network structures because you're just increasing the number of nodes in the network and also affect the network topology analysis results. Secondly, past literatures have shown a variety of input data that has been used to construct networks for multiple purposes. This could be related to the scoping during the context establishment, which is the first uncertainties I've mentioned before. Those diverse types of input data, for example, a risk register or an accident report, left a gap for understanding the relationship between the types of input data and the corresponding network topology results. And finally, a network with nodes represents risk, their causes and consequences is actually providing a risk landscape. And to note difference of two networks represents as a risk assessment and an accident report on the same system might help to characterize the uncertainties regards to the completeness in the risk management process. Because if a missing risk event or a missing link between two risks is the inherent cause for an accident, in that way, by studying the differences in the network analysis results could help to identify and reveal more insights into that accident. So the whole PhD project will be formed as this graph. By achieving the last slice objectives, which is its sensitivities and uncertainties, some common sources of uncertainties in the risk management process can be characterized using the network method. And the final thesis will be able to claim how exactly is the complexity with the integrating context issue being sources of uncertainties embedded within the risk management process. And that's all for my thesis descriptions. Thank you for your attention.
Well, thank you very much for that, Yifei. That's fascinating stuff with some topological risk analysis. If anybody's interested in learning more about this as well, there was a great presentation given by Dr. Cameron Huddleston Holmes of the CSIRO here at the Sustainable Minerals Institute at UQ. He presented on using this methodology to look at the risk analysis for the Beetaloo Basin gas project. So it's a great talk, and it's online on the YouTube channel. So we have a little time now. Do we have any questions? We have a question in the chat box. No, not a question in the chat box, but somebody saying thank you. That was a fantastic talk.
Thank you. Enormous attendance.
So do we have any questions for Yifei?
I've got my hand up.
Oh, sorry, I didn't see that, John. Go ahead.
Yeah, no, just a great talk. Just from a management perspective, you know, having managed the odd company or two across multiple jurisdictions with different nationalities, and what I've found is that risk node analysis approach is really fantastic. It forces you to identify all the areas of potential environmental risks or health and safety risks, etc. And what I have found is that the greater the granularity, the more risk nodes that you identify, the greater the certainty you might be able to avoid something nasty. It does add a significant a load to managing a business. But what I did find was extremely useful was that even at each of those nodes, didn't matter where it was in the business, a very simple one-page report which gave no scope for long-winded discussion, but literally tick boxes that address the perceived risks for that particular activity. And people were putting these in every day. And the benefit of that was that it highlights in their own minds on a continuing basis what the risks are. And it makes it extremely difficult for them to avoid reporting further up the management chain. So just a little personal experience.
Thank you so much for sharing that.
Yeah, I'd just add to John's comments there to say this methodology is really the best way that we currently have of identifying the sort of cascading failures that you might get in complex systems, like all of the ones that you described at the start of your talk, where a number of small potentially, well, you know, not necessarily obviously connected, things all going wrong at the same time connect and cause a catastrophic failure. But each one of them by themselves might not be a significant risk. And certainly the software that Kanata uses to visualize and look at these risks, I can't recall, what is the software that you use called?
It's Python based, but yeah, it's network is its library name, but it's still under, yeah, it's still under formalization, but due to the time limitation, I could not describe it in more detailed way. Probably next time I will just share more of the software itself. So, yeah.
Fantastic. Well, thanks very much for that, Yifei. It's looks like we don't have any more questions here, so we'll move on to our next speaker, Avish Kumar from JCU. Avish is a PhD student at James Cook, and he is talking about the genesis of copper mineralization at the Balgammon deposit in North Queensland. Please take it away, Avish.
Hi all. Yep, so you can hear me now?
Yep, all good. Hear you and see you.
Okay, that's good. Hi all, I'm Avish, and I'm a final year PhD student at, as Tom mentioned, I'm at James Cook University. And I'll be talking about the genesis of copper mineralization at the Balgammon deposit. It's not just the Balgammon deposit that I'll be sort of looking at. I'll be looking at this other deposit called Isabel. And basically this project sort of came from a broader sort of a project on critical metals, where we were looking at indium in Balgammon and Isabel deposit. And all the work was funded by GSQ basically. So for this work in particular, so my supervisors are Ian Stanislav and Paul Dex, and we also collaborated with Laura Martin from the University of Western Australia. So he's an expert in SIMS, and we did some sulfur isotopes to actually figure out the genesis of this deposit. So the aims of this deposit, as I sort of mentioned early on, so we'll be looking at the source of this mineralizing fluids. So these are basically tin, tungsten, and copper deposits, and what we're trying to sort of figure out if the source of the fluids will tell us, in the sense like if they're truly a magnetic hydrothermal deposits, or do they have like some other fluid signatures such as connate fluids or basinal fluids sort of interacting with the mineralizing fluids. And I also did some geochemical modeling of these fluids. So basically I'm looking at the conditions such as the AH and the pH that might be involved when sort of these fluids mobilize and deposit or will form your chalcopyrite or sphalerite. And then I also sort of looked at the analyzed this sulfide phases mostly for trace elements. So in brief, just the geology of this my study area. So this is the regional scale geology of the Northeast Queensland, and the sort of origin we're sitting in is the Mosman origin, highlighted in blue over here, and the oldest unit in that origin, which is the Hodgkinson's formation, and it is a meta-sedimentary unit, and that gets included by this O'Brien's Creek supersuite. So this O'Brien's Creek supersuite are the rocks that sort of form your tin and your tungsten deposits. They're fairly reduced. And then later on, we have this almadine supersuite. And there's slightly a mafic end member of this a suite of granites that we see in this northeast Queensland. You also have this Udan supersuite. And from what we have sort of looked at, this unit actually is not mineralized at all. And in terms of the walking distribution that we have sort of looked at, we don't see any sort of walkings for sort of copper, tin, or any other polymetallics within this suite. But interestingly, we have this cool moon volcanic group that appears to have a more sort of oxidized magmatic signature to it, and they're the ones sort of that form the copper mineralization as we look at. So overall, you have this the Belgammon deposit, and if you'd like to know more about this deposit, you can look it up in Kumar et al. 2022. So you have the Hodgkinson's formation that gets intruded by the Slodayat-Creek volcanics. Before that, it's intruded by the Una porphyry, and the Una porphyry is what carries the tin mineralization. And that later on gets intruded by the Slodayat-Creek volcanics. So some example of this Slodayat-Creek volcanics are here. So this unit over here, which is the quartz feldspar porphyry, that includes the Hodgkinson's formation, and the quartz feldspar porphyry is what we think carries the sort of causes the copper mineralization. But early on, as I sort of mentioned about the Una porphyry carries the tin mineralization, and in terms of the paragenetic sequence that we see, so that is the tin mineralization that is cross-cut by these sulfides. So the sulfides are later than the tin. So in general, at the Belgammon deposit, we see these three types of sulfide textures. One is massive chalcopyrite and pyrrhotite with inclusions of sphalerite, and then the other one is this massive chalcopyrite with exsolutions of pyrrhotite. And so the exsolution textures actually occur in slightly deeper sections of this deposit, especially in the Una porphyry. And then you have this chalcopyrite and pyrrhotite textures, but with a rhomboidal pyrite. And these, you basically observe them in sort of the metasediments, the massive sulfides that are formed in the metasediments. So the Isabel deposit, a sort of similar style of deposit, but it is mostly zinc dominated. So you have the Hodgkinson's formation that gets included by this feldspar porphyry dike, and that what we think is that's what's causing the mineralization, especially the volcanics. And in terms of like sort of the mineralization itself, so you have this early cassiterite that is sort of overprinted by sulfides, and we dated this cassiterite to roughly around 314 million years. And a little bit more about the mineralization at the Isabel deposit. So you have this this sphalerite that is cross-cut by chalcopyrite and pyrrhotite. So I'm emphasizing on the this chalcopyrite and pyrrhotite is because that's where we measured the sulfur isotopes to sort of study the source of fluids that are involved. And then the other sort of the texture that we see is that sphalerite with this chalcopyrite disease. So there are two types of veins. One is sphalerite based mostly, and the other one is sphalerite in galena. So the trace elements in the Belgamen deposit, in general, if you look at indium, the sphalerite is enriched in indium, and then there's this chalcopyrite. We start to see that the pyrrhotite is enriched in cobalt, and silver is enriched in chalcopyrite. And gallium, germanium is sort of basically in trace amounts in most of these sulfides. In the Isabel deposit, we start to see that so there's a mineral called sternite, which I've highlighted over here, sort of placed over here, and that tends to have a lot of indium. So sternite forms by altering cassiterite. So as cassiterite is sort of formed, and then later on the sulfides come in, it alters the cassiterite into sternite. And we tend to see that this sternite is enriched in indium. And in this deposit in particular, you start to also see that the indium is enriched, the sphalerite is enriched in indium as well. So the cobalt is in trace amounts, and silver in particular is sort of goes to galena, which I haven't sort of shown you over here. And germanium is also in trace amounts. So looking at the sulfur isotopes, and the sulfur isotopes were conducted on the chalcopyrite and pyrrhotite that I sort of showed earlier on in the presentation. So at the Belgamen, where I've showed you the two massive sulfides, they're roughly sort of don't plot on this kinetic fractionation line. So this kinetic fractionation line was derived from Kajiwara and Crows. That sort of tells us that they formed in this equilibrium, and it sort of makes things a little bit clearer because we start to see this exolution textures, exolution of pyrrhotite in this chalcopyrite. So that sort of tells us that, yeah, okay, that they might not have formed in a sort of equilibrium. But if you look at the chalcopyrite and pyrrhotite from the Isabel deposit, they plot on this 300 degrees kinetic fractionation line, and that sort of confirms it that a kinetic fractionation played a role in the Isabel deposit. So we sort of calculated temperature using three other methods, well, at least two other methods. So we used sternite and sphalerite thermometer, and that gave us a temperature of about 280 to 310 degrees Celsius for both of the deposits. And then we used mineral textures to actually calculate the temperature as well. And then the sulfur isotope was the other one. So that's why we were able to make these sort of interpretations that either the sulfides are precipitating out in equilibrium or in disequilibrium. So going back to what I mentioned earlier on in terms of if the deposit is truly a magmatic hydrothermal deposit, and in order to test that, what I did is basically look at the sort of the variation in the sulfur isotopes. So if you look at sulfur isotopes from modern and ancient sedimentary pyrite, they have a large variation in terms of about 10 parts per mil to about 30 parts per mil. But if you look at igneous rocks, they have a slightly lower variation. So the variation that we're looking at over here is roughly around 0.5 to 2 parts per mil, so and which sort of confirms it in that these fluids were magmatic, especially the sulfur was magmatic. Looking at the geochemical modeling, so I think I'm basically sort of running out of time now, and I'll just highlight a few things, such as if you look at indium in the system, we start to see that indium forms in a slightly acidic environment, roughly around between pH 2 and 3 at about 300 degrees Celsius. compared to other metals that might form, such as chalcopyrite or pyrrhotite. So the mineralization model, so what we sort of, when we compile everything together, we start to see that the magmatic episode from 310 to 280 million years is when the sulfides sort of came in during a event of like crustal thinning. And then we draw the conclusion that the source of the sulfur was magnetic as well, because the values are so constrained. And so we studied these two deposits, which is the Belgamet and the Isabel deposit. And looking at the mineralization, we sort of draw the conclusion that the Belgamet deposit might have formed at a slightly greater depth compared to the Isabel deposit. Sort of highlighting that in terms of polymetallic deposit in general, you tend to form your copper deposit closer to the intrusion, and your sort of zinc polymetallics are slightly far away from the intrusion. And these sulfides are enriched in indium as well. Thank you. That's all that I have for today. And also thanks to GSQ for funding this research.
Thanks, Avish.
Oh, you good, Matt?
Sorry, Tom. From the co-host, you never know who's going to take over. Thank you very much, Avish, for that. Do we have any questions for Avish about his work? I know Avish has presented a couple of times in GSQ forum, so people might have already got all their questions out with you already, Avish. But any questions? Feel free to raise your hand, and we can promote you to speak, or you can ask a question in the chat or the Q&A box. Actually, quickly, I'm going to steal the limelight for 1 quick second while people are thinking about any questions. And just announce that we have set a date for Digging Deep 2023. So we have one more presentation today, but I just thought I'd get in here before that last presentation. We have a set a date for Digging Deeper 2023. There's a QR code there if you wish to scan that. Tickets are now available. It is a free event. I would encourage anyone who's in Brisbane to join us in person in Brisbane for that. There will be other workshops potentially around that, looking at some core at the Exploration Data Centre. They'll be announced closer to the date, but there'll be a full line of presentations on the GSQ projects done under our New Economy Minerals Initiative, as well as our Queensland Resource Industry Development Plan programs. There'll also be a student presentation session, student poster session, sorry. So I'd please encourage you to join us there. We are going to record those presentations, but we're not going to live stream at this time. We've had some issues with that in the past. So we're going to record the presentations and then share them out afterwards. So we wanted as many people to join us in person that can. But I thought I'd just quickly get into that before. And I didn't share that screen at all, did I?
I've got a few minutes as well. Matt, I'll just do a shameless plug too early on. Every deposit that's been mentioned so far in a talk today has a chapter written for it in the Queensland Deposit Atlas series. So with Ernest Henry, Osborne, Mount Garnet, Mary Kathleen, and Bale Gammon. If you're interested in learning more about any of those deposits, jump on and check out the Queensland Mineral Deposit Atlas series. It's a collaboration between GSQ and the Sustainable Minerals Institute. Very good little potted data sets and a reading that you can do on each of them.
All right. Well, thank you for giving us that opportunity there by finishing it early. Thank you as well for Jenna McGovern, who's our last presenter today. So Jenna is from the University of Queensland. She's talking about lead zinc mineralisation in the Canning Basin and Western Australia. Thank you for sticking around, Jenna, and for letting Tom and myself have a little bit of a chat in between there. Please take it away.
Oh, good. No, thank you for hosting. Let me just share that one. Cool. So I'd like to start just by acknowledging the traditional owners. I'm presenting from Mianjin, Brisbane, where the traditional owners are the Turrbal and Yagara people. So I would also like to thank my supervisors and the companies that sponsor my research, SEPA Resources and Buru Energy, and the Geological Survey of WA for their ongoing help, and Geological Survey of Queensland for making today happen. So we have a growing need for a wide range of energy transition metals needed to reach net zero. And the future demand of energy technologies and emission targets globally have seen both base metals and a range of other metals become increasingly hot commodities. Zinc and lead in particular are used in a wide range of ways in manufacturing, and increasingly with zinc in flow batteries and new battery technologies. So my project aims to provide new tools for understanding their emplacement in an underexplored area of Australia, in developing and validating novel exploration tools that we can apply, hopefully, in a wider range of geological settings like Queensland. So the main metals that I'm focusing on come in the form of sphalerite, which is a zinc sulfide, and galena, which is a lead sulfide. But along with these zinc and lead sources, they have a range of other metals that can be associated with these ore minerals, depending on the conditions. So I'm looking at the Canning Basin, which is in northwestern Australia. And it has a maximum sediment thickness of 15 kilometres, which is concentrated in that big blue strip through the northeastern component. And I'm particularly interested in a few of those sections. So the big blue section is the Fitzroy Trough. And on either side of it, to the northeast, you have the Leonard Shelf. And to the southwest, you have the Barbed Wire Terrace. So these are two areas where they're separated from the Fitzroy Trough by large fault systems. So the Leonard Shelf and Fitzroy Trough are separated by the Pinnacles fault system. And on the southern end, we have the Fenton fault system. Why focus on this area in particular? Well, on the northeastern side, we have a few known lead zinc deposits. These haven't really been looked at much in the last few decades, and they have carbonate hosts, low temperature mineralization, and over here we see some outcropping, which is, as a lot of us may know, a big factor in where we've seen deposits is where we also have outcrop. So on the southern side of the Fitzroy Trough, we have the Barbed Wire Terrace, which is undercover without outcrop and coincidentally has no known deposits. However, it does have some historic core data, and those blue dots that I've shown on the map are hyperspectral imaging done on historic core. So we have a pretty good amount of data, although sparse coverage over a large area, to actually get an idea of what's going on the Barbed Wire Terrace and maybe why we aren't seeing mineralization there, or where it is if we haven't found it yet. So this is just to give an overview of the deposit style and the stratigraphy. So this is a model from Wallace et al. In 2002 that shows the basic idea behind how these deposits formed on the Leonard Shelf. You have compaction flow and hydrocarbon generation happening within the Fitzroy Trough. This is forcing fluids up along that Pinnacle fault system as a fluid conduit, and then depositing the lead and zinc metals that are coming out of the trough into the Devonian age carbonates. Now, these are very old sections that I've pulled together to kind of give an idea of what it's looking like if you were looking from the south, looking up towards through the trough. So that was the Leonard Shelf on the right there. You've got the Fitzroy Trough, which has a huge amount of sediment, really well preserved strata. But then on the Barbed Wire Terrace, we only have a little bit of these same Devonian carbonates preserved due to erosion through uplift. But we want to find a deposit there. And if that's the case, we want to be looking along faults and in these Devonian carbonates if it follows the same ore deposit style as what we see on the Leonard Shelf. So the known deposits are hosted, as I've mentioned, in the Leonard Shelf, in the Devonian age carbonates. And Unusually, they are a similar age, the host rocks are a similar age to the deposits, and this doesn't happen very often in similar deposits worldwide. We do, over to the west, which I haven't shown, have another large lead zinc deposit, which is hosted in the Ordovician carbonates, and it is younger and more typical of the model. However, special in its own right. I just won't be focusing on it today. So sphalerite has a lot of fantastic applications. Its geochemistry can vary significantly depending on a range of measurable factors. And it's been established that sphalerite can act as a geothermometer using a suite of trace elements, which is that GGFMI. So that's gallium, germanium, iron, manganese, and indium in some cases. Sometimes the I doesn't get a mention. So basically using this as a geothermometer, and based on what's known about how and why sphalerite geochemistry changes depending on deposit type, the Canning Basin is a prime candidate to produce sphalerite that is significantly enriched in gallium and germanium, which are two metals of interest in the new economy, due to the ore-forming fluids being estimated to be only around 70 to 90 degrees, which is quite low, especially compared to some of the other talks you've heard today where zinc mineralization can happen at around 300 degrees. The poor lead sulfide gets a bad rap, galena. It has a bit more of a mixed bag and does have potential to host additional metals, but some of these are often considered to be value detractors like cadmium because of the environmental risks it presents to process those materials. It can also present analytical challenges due to the high and variable lead composition, which can interfere with some of the more highly sensitive analytical equipment that I hope to use. It's just worth keeping that in mind. It is a limiting factor sometimes. So I'm basically trying to understand the sphalerite geochemistry and the basinal fluid fertility in the Canning Basin. So this is looking at all of the different episodes of fluid that are moving up through those big fault systems and trying to identify or fingerprint which fluid sources were carrying lots of metals and which ones weren't. Can we find a really simple method that exploration can use in order to know quickly whether or not they are near a ore-forming system? So first of all, I need to understand the role of hydrocarbons in fluid fertility. So like I showed in the Leonard Shelf ore deposit model, it's known that hydrocarbons do play a role as they're also maturing in that basinal compaction and moving with these same fluids. So there is a link between these two fluid types, and we'd like to know more about why that is the case. I also want to know whether or not the trace elements seen in sphalerite throughout the Canning Basin fit the trends identified in previous literature, and whether or not this trace element composition points to an economically viable amount of any of the critical metals that are often associated with sphalerite. And then last, I just want to identify whether or not there's any relationships between metal enrichments and deficits that might be able to be seen in the carbonates, and therefore inference is able to be drawn even if you don't intersect a mineral system in a particular drill core. And just to throw up some pretty pictures on what these analyses will look like, the rocks will be sampled in a few months, but on the left there, you've got some microscope images of Leonard Shelf carbonates with sphalerite precipitating along with a second generation of calcite, just along a boundary of a grain. And then you can see that in cathodoluminescence in red there on the side, along with some fluid inclusions, highly complicated fluid inclusion environment. But we will be able to hopefully tease out some end members of these to get an idea of what the different fluids look like in relationships to hydrocarbons. Then on the right there, we've got some gorgeous laser ablation ICP-MS maps. So these show the metal distribution within a single grain of sphalerite. And this is actually done in Mount Isa. So this is a very recent study by Liu et al. 2022 that utilizes sphalerite's very interesting geochemistry as a way of understanding deposit mechanics and fluid fertility. And so that was something that came out recently. It was very exciting to read about while I was doing my literature review. More broadly, the applications to Queensland. So there are a lot of zinc deposits in Queensland. You can see this image from Geoscience Australia, just has the operating mines shown in a dark blue and the known deposits shown in a lighter blue, and Queensland clearly has the most. And as we've heard of today, Mount Garnet and Balgamon as well, both have pretty interesting settings with having highly fractionated granitoids associated with them, as well as that Hodgkinson formation, providing very interesting source of metals potentially that could definitely be further explored and obviously is being. So in essence, I want to know whether or not the relationships in sphalerite geochemistry specific to the system we predict we're in can help vector to a deposit and understand the metal mobility in the fluids coming out of the Fitzroy Trough. I'm hoping I will be able to understand sphalerite trace metal geochemistry along with its potential to host critical metals and explore whether the trace elements in the sulfides, particularly sphalerite and pyrite, will vary with distance from a deposit. So are there depletions within sphalerite that can fingerprint sulfide precipitation that's not associated with the deposit as well? Thank you very much. Yeah, do you have any questions?
Thanks very much for that, Jenna. That was fantastic. Open the floor up to questions for Jenna. I'll just fire one off quickly while people are marshalling their questions. That slide with the compositional photomicrographs on there, or as scanning SEM images, I assume they were. That looked like the critical elements. So if you can just scroll back to that slide.
Yeah, sorry, it froze on me for a second there. There we go.
So gallium, indium, germanium, or less so germanium, but yeah, potentially. That they all look like they're very closely related to each other in the sphalerite, but they also look like they, and mercury weirdly, and tin, they look like they post-date the sphalerite in some sort of later event that's coming through. This is the first time I've seen any images like that, and I've always, I've wondered about that association between those weird metalloids and zinc. Do you know anything about how and why they're there? Or have you sort of addressed any of that or come across any of that in your readings?
Yeah, well, I guess more broadly in understanding sphalerite and how different metals come in or out of a system. It's a mineral that's quite fickle. Things that it will hold on to in some conditions, it will let go of quite easily in others. So it's very, it's able to change its chemistry based on subsequent events coming through, which I guess one of the things that I think could be applicable in Queensland, particularly with these higher temperature deposits, is that you might actually have more distal halos of the enrichments of these other metals that have essentially just been pushed out of the ore metals in the deposit and emplaced elsewhere. I haven't read a whole heap on that because I am focusing mostly on low temperature systems, but theory is definitely there and there's a lot of research on it. Some of which is done in Australia, a lot of which is done elsewhere. So someone should definitely chase it down.
Oh, no, there's quite a bit of buzz around the critical metal space about all of these little weirdos that hang out in sphalerite. So yeah. So do we have any more questions for Jenna? No. Thank you very much for that, Jenna. We'll open up if anybody has any more questions for any of the other participants that they've thought of subsequently. You can raise your hand or fire away. I've, at the risk of, holding the microphone, I've got a question for Alanis. If you, about about the relationship between the copper mineralization that's all around there, so the all around Mary Kathleen, so Jubilee, Mount Colin, Elaine Dorothy, all of these, you know, little shear hosted, or in the case of Elaine Dorothy, a little bit different, but pyrrhotite chalcopyrite dominant deposits, that sort of ISCG structurally hosted deposit. What do you think is different at Mary Kathleen? Like, why do you, in the shear zones there, and where we're getting brecciation around the shear zones, do we get like apatite? Oh, not apatite, sorry, epidote, rare earth rich epidote growing. I mean, there's a little bit of copper in there, but what do you think's like? Do you think there's some fundamental difference between what's going on at Mary K and what's going on at these other copper prospects around the place there?
You wanted to go with a hard question and a big question. So for the purpose of my PhD, I'm not really focusing on any of that copper mineralization, but I will be looking into it in a little bit more detail, especially to look into whether or not potentially we have like an evolving fluid system happening through Mary Kathleen. So you've got Mount Colin, which is a basically like a vein hosted copper gold system in calcite and then quartz, which is all on the same lithological contact as Elaine Dorothy and as Mary Kathleen. And so then Elaine Dorothy has allanite, so it's also got rare earth elements, uranium, copper and gold, whereas then Mary Kathleen only has uranium and rare earth elements. So it's maybe too much of a coincidence that they're all kind of lying on the same structure, potentially all linked to this shear zone. So I haven't looked into it in much detail, but that will be one of the aims of, you know, the kind of like a broader trying to link everything together within the syncline. So it is very interesting, and I don't know yet is the answer.
Oh, it's such a fascinating area. And another place, I don't know if you've had the chance to get up there and have a look around, but if you do, you've got to go and see Tribulation Quarry up to the north of Mary Kathleen.
Yeah.
A big calcite pod up there with giant actinolites and epidotes in it, sort of meter wide calcite crystals that are just sitting there.
Yeah, I've been to the pod just north of Mary K. Is this one, is it a bit of a drive, or is it?
Yeah, it's a little bit of a drive up to the north. Lucas Marshall did a PhD at James Cook on it with Nick Volker in about 20 years ago, I want to say. But yeah, definitely worth a look if you go up there. Just spectacular.
Well, I'm heading out in 2 weeks, so I'll put it on my to-do list.
Take a ute and a big hammer.
Yeah, got them. That's all right.
So do we have any other questions in the chat, Avish?
Yes, I have a question for regarding the Garnet geochemistry for Jin.
Hi. Oh, sorry. I just.
So regarding the European anomaly, so some of the garnets tend to have like a quite like a positive European anomaly, and and some have a negative anomaly. I was just wondering what could be sort of controlling that? Is there like a redox control on it? Because in sort of in systems, you're in a very reduced system.
Yes, there are many ways, like many factors can control that, the positive European anomaly and negative European anomaly. The main factor I found is that the temperature can actually influence, and the redox condition, and can also influence on these, like European goes into the garnet crystal. Maybe I can share my screen again, because I have slide for that, just in case somebody ask. And is it coming out?
Yep.
Okay. slowly loading. Okay. So here you can see the ratio of the for these different types of garnet. So if you have like large European anomaly to like Syrian anomaly, you tend to like you tend to have a more redox environment, whereas like you have lower ratio, you tend to have more reduced environment. That's how these are gonna tell you. Happy this solved the question.
No, it did actually. Yeah, I mean that's what I was thinking. Why do they have like such a different anomaly patterns? I guess the other question is your Garnet also have tin anomaly, is it?
I would
I'm not really
go back.
familiar with Garnet trace element chemistry, but
Yeah.
is there a common thing in Garnet from sort of tin deposits?
Sorry, can you just repeat your question again? I didn't really catch that.
Oh yeah, so I was just wondering, the other thing I was wondering about the tin anomaly that you have.
Oh, yeah, tin.
Yeah. So on the plots A, C, and E, I think.
Oh yeah, that's the concentration. So it
Okay,
shows
right.
like in ppm for the tin. So normally like if you have like an environment, you have the fluid contains lots of tin, and the tin can really goes into the garnet itself. So it's just like if your garnet contains a lot of tin, it really means that the environment, the fluid contains a lot of tin.
Okay, thank you.
That's a good.
Might just jump in quickly here and share my screen. This, yep, that's the one. So just to remind everyone about digging deeper, we have a slide here. Is I hope you can. I'm sharing the right screen. I've got lots open at the moment, but digging deeper is a fantastic event. It's held at the end of the year in Brisbane. There's a huge range of topics that are going to be covered in it. It's free, and if you're interested in learning a bit more about it, you can quickly scan that QR code that's on screen, and it'll take you to the website to advertise it. But it's a great networking event, and there's drinks and what have you on afterwards as well, which it's very fun. So hopefully we'll see you all down there in November, or down here in November for digging deeper. Do we have any more questions for any of our panelists today? Or any more general chit-chat?
Thank you so much to Tom and Matt for hosting this afternoon. It's been great.
Thanks, Alanis, and thanks to Evan for his very efficient wrangling of everything behind the scenes as well. It'd be anything that I touch and have to do all that wrangling turns to custard pretty quickly. So Evan's there giving me reminders that stuff's on and what have you. So
no, you've done well, Tom. Thank you.
Well, I think that's everything today. Might wrap it up there. But once again, thanks to all the presenters for a great series of talks, great diverse range of topics that we looked at, and some really interesting things to think about and go on further with. And good luck in all of your studies. It looks like you're all getting reasonably close to the business end of your PhDs. You certainly look like you're on top of stuff, but great talks from everyone today. Thanks very much.
Thank you so much.
Hopefully,
Thank you.
Thank
next
you.
week, next month, we'll have another one of these sessions. Topic to be advised. I think
I can help you out, Tom.
Yep.
Yeah, so Thursday, the 28th of September, Indigenous dealings with exploration. So we'll have a panel of Indigenous presenters sharing their experiences with mineral explorers and cultural heritage and those sorts of things. So a really fascinating discussion afoot in 4 weeks' time. So look forward to that one.
Oh, fantastic. Sounds excellent. Very good. Well, thank you, everybody, and we'll see you all on the 28th next month, if not sooner. Cheers, guys.